The world of quantum mechanics is a peculiar place. One of its most baffling concepts is the observer effect. This is the strange idea that the very act of watching something can actually change it. It touches the fundamental nature of reality itself. This principle is a cornerstone of quantum theory. It forces us to question our classical intuitions about an objective world. The universe, it seems, is not a passive stage upon which events unfold independently of us. We are, in some profound way, involved. Imagine you want to measure the air pressure in a bicycle tire. To do so, you attach a pressure gauge. The act of connecting the gauge inevitably lets a little bit of air escape. So the pressure you measure is slightly different from what it was before you tried to measure it. Your measurement has disturbed the system. This is a simple everyday analogy for the observer effect. But in the quantum world, the situation is far more mysterious and profound. The very act of gaining information about a quantum system seems to fundamentally alter that system. Quantum mechanics is the science that describes the universe at the smallest scales. It deals with atoms, electrons, photons, and other subatomic particles. These tiny entities behave in ways that defy common sense. For instance, they can exist in multiple states or places simultaneously. This is known as superposition. They can also exhibit characteristics of both particles and waves. This is called wave-particle duality. The act of observation seems to force the particle to make a choice. Prepare to have your intuitions challenged. The double-slit experiment is perhaps the most famous demonstration in all of quantum mechanics. It beautifully illustrates the strangeness of the quantum world. Imagine you are firing tiny particles, say electrons, one by one towards a detector screen. Between the electron gun and the screen, you place a barrier with two narrow parallel slits. If electrons are like tiny bullets, we would expect to find two distinct bands on the screen. However, when we perform this experiment without trying to determine which slit each individual electron passes through, something astonishing happens. The electrons, fired one at a time, gradually build up an interference pattern. This implies that each single electron goes through both slits simultaneously, like a wave, and then interferes with itself. Now here comes the part that truly highlights the observer effect. What happens if we try to find out which slit each electron actually goes through? The moment we implement such a which path detection scheme, the interference pattern completely vanishes. Instead of the wave-like interference, we get the two simple, distinct bands on the screen. The act of observing forces it to behave like a particle. How does the electron know it is being watched? This experiment encapsulates the core mystery of the observer effect. The universe, it seems, behaves differently when we are looking. So, what exactly constitutes an observation in the context of quantum mechanics? Any interaction that extracts information from a quantum system can act as an observation. This interaction could be with a sophisticated measuring device or something as simple as a stray photon of light bouncing off the particle. The essential feature is that the quantum system becomes entangled with something else in its environment. Think of a quantum particle existing in a state of superposition. When this quantum system interacts with a measuring apparatus, this inherent blurriness resolves. The particle chooses one definite state from the many it previously embodied. This process is often referred to as the collapse of the wave function. To see an electron, for instance, we might need to shine light on it. A photon of light would then strike the electron. This interaction allows us to gain information about the electron's position. However, the photon also imparts some of its momentum to the electron, giving it a kick. This is intimately related to Heisenberg's uncertainty principle. Observation, by its very nature, involves interaction, and interaction in the quantum realm necessarily causes change. Does human consciousness itself play a special, unique role in causing the collapse of the wave function? Some early pioneers of quantum mechanics thought so. Physicists like Eugene Wigner proposed that consciousness is not just another physical process. He suggested that the wave function only truly collapses when a conscious mind becomes aware of the outcome of a measurement. This is a rather provocative and anthropocentric idea. It places human awareness at the very center of the process of reality creation. However, the majority of physicists today find this idea problematic. The prevailing view in modern physics is that any sufficiently complex macroscopic interaction can lead to a process called decoherence. Decoherence is the process by which a quantum system loses its distinctly quantum properties due to its entanglement with the surrounding environment. A conscious observer isn't strictly necessary for the mathematical formalism of quantum mechanics to describe this process. Quantum mechanics is an incredibly successful theory. Its mathematical framework makes predictions about the behavior of atoms and particles with astonishing accuracy. Yet, despite its predictive power, what it actually means for the nature of reality is still fiercely debated. This has led to the development of numerous different interpretations of quantum mechanics. The Copenhagen interpretation is one of the oldest, and for a long time was the most widely taught. It was primarily developed by Niels Bohr and Werner Heisenberg in the 1920s. Essentially, it advises a pragmatic approach. It says that quantum mechanics only describes what we can measure about the world. We shouldn't ask what a particle is really doing when we are not looking. The act of measurement itself creates the property being measured. Then there is the many worlds interpretation, proposed by Hugh Everett III in 1957. MWI asserts that the wave function never actually collapses. Instead, every time a quantum measurement is made, the entire universe splits into multiple parallel universes. All possibilities described by the wave function become actual realities, each in its own separate world. QBism, which stands for quantum Bayesianism, offers yet another perspective. QBism suggests that quantum mechanics is not a direct description of the objective world itself. Instead, it is a theory about an agent's beliefs, knowledge, and expectations about the world. The wave function represents an observer's personal, subjective degree of belief about the possible outcomes of future measurements. Consequently, the collapse of the wave function is simply the observer updating their beliefs based on new information obtained through a measurement. The deep mystery of what quantum mechanics truly tells us about the nature of reality continues to fascinate and perplex. The brilliant physicist John Archibald Wheeler devised a series of thought experiments, one of the most famous being the delayed choice experiment. This experiment is even stranger and more counterintuitive than the standard double-slit experiment. It seems to suggest that actions we take in the present can influence events that have already happened in the past. Variations of Wheeler's delayed choice experiment have been successfully performed in laboratories, confirming its bizarre predictions. In a typical delayed choice experiment, we have particles, such as photons, heading towards a double-slit apparatus. We allow the particle to pass through the region of the slits. It is only after the particle has notionally made its decision to act as a wave or a particle that we make our choice. We decide whether we want to acquire information that would tell us which path the particle took, or to erase that which path information. The astonishing result is this. If we choose to find out which path the particle took, it behaves as if it went through only one slit, no interference pattern. If we choose to erase the which path information, the interference pattern suddenly reappears. It is as if the particle, back when it was at the slits, somehow knew what choice we were going to make in its future. This does not mean that we can send messages backwards in time or change history. The resolution of this apparent temporal conundrum lies in understanding that the erasure of which path information involves carefully correlating different sets of measurements. The full picture only becomes clear when all the data from all parts of the experiment are brought together and analyzed. The delayed choice experiment highlights the non-local and contextual nature of quantum mechanics. So, what does all this quantum strangeness, particularly the observer effect, mean for us? The observer effect suggests something truly remarkable and deeply significant. It indicates that we are not merely detached, passive spectators looking out at an independent and pre-existing universe. Instead, we are active participants. The act of observing, of measuring, of gaining information is not a neutral process. It is an active engagement, a process that seems to be intricately woven into the very fabric of reality itself. This represents a radical departure from the worldview of classical physics. Quantum mechanics reveals a universe that is far more fluid, more dynamic, and more responsive. It paints a picture of a cosmos where the boundary between the observer and the observed system becomes inherently blurry. We are part of the system we are studying. This does not mean that our everyday thoughts can directly shape physical reality in some kind of magical or telekinetic fashion. The observer effect primarily operates at the quantum scale, influencing the behavior of subatomic particles. However, it does imply a much deeper and more fundamental connection between ourselves and the universe than classical physics ever envisioned. Our interactions, our measurements, our relentless quest for knowledge. These are not separate from the universe's ongoing evolution. We are intrinsically linked to the phenomena we seek to understand. The observer effect remains one of the most profound and persistent mysteries at the heart of quantum mechanics. It consistently challenges our most basic, ingrained assumptions about the nature of reality. It forces us to reconsider our understanding of space, time, causality, and the role of information in the physical world. We have journeyed through some of its most striking manifestations, such as the double-slit experiment and the delayed choice scenarios. We have also touched upon the various interpretations that physicists have proposed, from the pragmatic stance of the Copenhagen interpretation to the mind-boggling proliferation of universes in the many-worlds view and the agent-centric perspective of QBism. Each of these attempts to make sense of the quantum puzzle, but the puzzle itself is far from being definitively solved. What has become increasingly clear is that information itself is a key player in the quantum drama. The act of gaining information about a quantum system is inextricably linked to how that system manifests. This strongly suggests that reality, at its most fundamental level, might not be primarily about matter and energy in the classical sense, but about information. The implications of this information-centric view of quantum reality are vast and extend far beyond the confines of physics laboratories. They ripple outwards into philosophy, into our understanding of knowledge, and into our very conception of ourselves and our place in the universe. If the act of observation, of acquiring information, actively shapes the reality we perceive, what does that truly say about our role as observers? It suggests we are not merely passive inhabitants of a pre-existing, fully formed world that we simply uncover piece by piece. Instead, it paints us as active participants, perhaps even co-creators in the universe's ongoing process of becoming.